In this video, we're going to be finishing our investigation of alternating series by looking at the alternating series error bound. So I think first I need to be specific about what I mean by an error in the first place. Because we're just at this point kind of saying, well, okay, we can apply the alternating series test to determine if an alternating series converges. We can also determine if a series is absolutely or conditionally convergent based on what we've learned recently, but we haven't really been doing much with like a value. So suppose we wanted to approximate the value of the natural log of 2 with the power series we looked at before, right? Where we had this natural log of 1 plus x being the sum from 1 to infinity of negative 1 to the n plus first times x to the n all divided by n. And, we plug in 1 for x, and we get that alternating harmonic series, which, at least when it's arranged that way, is going to converge to the natural log of 2. And when we were talking about the alternating series test in the first place, we made a diagram kind of like this one, where we were tracking the partial sums of the alternating harmonic series. And if I bring in that table right there, that's kind of the table that we were looking at. Like, say, the second partial sum, where I added 1 minus a half, that gave us a total of a half. And if I did 1 minus a half plus a third, that gave us the third row, which was 0.833. We saw that, as we added more terms, we had a whole lot more terms in that video, but we saw we were converging on the natural log of 2. And I'm going to, plot that value with that blue horizontal line, because that's going to be important for us. Now, it wouldn't be a very good approximation if I was to approximate the natural log of 2 using just one term of that infinite series. But if I did, that's what that orange bar there is representing. Okay, I've got, say that's the error in approximating using one term. And if I had approximated using two terms, take that away and talk about what happens if I approximated using two terms. Well, I'd have gotten over here, and then, that would be my error. Okay, and if I had approximated using three terms, I would have error looking like right there, and, so on. I could just keep doing this and keep labeling my error with higher and higher terms. But we see that the more terms we add, the smaller the error is getting. And, if I needed a numerical value, I could go over here and say, well, I could say, what's the difference between f of x1 and natural log of 2? Okay, and then that would fill in my error here, and that would give me the length of these orange lines, which are getting shorter and shorter. Sometimes they have a positive length, sometimes they have a negative length, because sometimes I'm overestimating and sometimes I'm underestimating. But what's going to be important for me to point out to you is to look at like kind of the movement between the black points, as we add more terms on. For instance, like when I go from the first partial sum to the second partial sum, I am subtracting a half. And that distance of a half that I went is definitely farther than the length of the orange line. And then when I go again and add the next term, which would be adding 1/3, okay, I'm going to overshoot the true value, the value I'm converging to. And that overshooting idea, that's pretty much the key idea with the alternating series error bound. And again, if I look at the error, if I had stopped after three terms, that would be the last orange bar you can see right now. That distance is not going to be as far as this distance where I'm about to be subtracting 1/4. So if I, for instance, wanted to approximate the natural log of 2 with the first four terms, you can see that the error would be right there. The point I'm making is that the next term will be larger in size. Okay, whoops. No, that's not what I wanted to show. There it is. Will be larger in size than the error. So where I'm adding this 1/5 right here, that 1/5 is going to be bigger than the error. So we have an error bound, a number that is bigger than our error, if we just look at the absolute value of the next term. And that's really going to be the idea for us with alternating series error bound. So this is the relevant theorem. Okay, if we've got an alternating series that converges to S, then that absolute value of the difference between S and a partial sum is no more than the absolute value of the next term. And it's the absolute value because the alternating part was the -1 to the k, and then the ak is just the positive part of the series. And so that's where we'll say error is less than or equal to the absolute value of the next term. And that note is going to be important for us, especially in AP Calculus. In order to apply the alternating series error bound in a free response scenario, we must first verify the convergence of the series using the alternating series test. So, for example, if we were looking at, the alternating harmonic series, which I'm not going to go into justifying its convergence, I'll do that down below. We've got a couple of free response examples. But if we were just going to use that same series in 9 terms, what's the alternating series error bound? So, when they say is approximated using the series above in the first 9 terms, what we mean is that we're going to do 1 minus half plus a third minus fourth all the way up, and we're going to stop at 1/9. And so there's going to be some error in not adding up all infinity of the terms, right? We're not going to get all the way to the exact answer. And, but we notice that this is an alternating series that's going to converge by the alternating series test. I changed my mind. I was going to copy in the justification. It's alternating with terms that decrease in magnitude to 0. That means it converges, and that means we can use the alternating series error bound. And that says that, okay, the error is no more than the absolute value of the next term, the first term that we didn't use in our, finite sum. Well, the next term would be negative 1/10, because I see the ones with an even denominator are the ones that are negative, so I'll just put a negative 1/10 in there and say, okay, the absolute value of negative 1/10, that's 1/10, and that's the alternating series error bound. Here's a multiple choice question I think would be good for us at this point. An alternating series is given by S. Okay, let S3 be the sum of the first 3 terms of the given alternating series. Of the following, which is the smallest number m for which the alternating series error bound guarantees that the error in approximating S using only 3 terms is m? Okay, well that means it would just be the 4th term. We're going to use the first 3 terms, so that's n equals 1, 2, and 3. So we're going to say our error is less than or equal to the absolute value of the n equals 4 term. So negative 1 to the 4 minus 1 divided by 4 squared plus 3, so that would be negative 1 over 19, so I'm going to take the absolute value of that and get 1 over 19 and have myself an answer. Another thing they can do is, can I ask you this in a backwards way? And so, how many terms do I have to add up to get the error underneath 1 over 500? And this is a little bit trickier. So I'm just going to remind you what we know is that, I guess that's probably not the order I wanted them in, but we know that the difference in S and Sn, that's the error, is no more than the absolute value of the next term. And so I'm just going to call an 1 over n to the 3, just like taking the absolute value of the terms kind of preemptively, not even worrying about the fact that it's alternating. And on these, my advice is just to be careful. Just go slow on these and make sure you're not just off by 1, because that's a really common error. So I'm just going to start with 6, the smallest answer choice I see. We're looking for the smallest value of n, so D is probably not likely going to be it. So we'll start at n equals 6. And so if we use the first 6 terms of the series, then the error is going to be the absolute value of the 7th term. So that error would be 1 over 7 to the 3rd. And, I don't know if you're like me, it's like I think I might know what that is, but I don't want to, do the wrong thing here. So I'm just going to write that as 1 over 49 times 7. Okay, and I can see that really 500 is 50 times 10, so this is definitely not, less than 1 over 500. So I'm just going to keep going. I'm going to try n equals 7. If I use 7 terms, the error would be the absolute value of the 8th term, so that would be, the absolute value of negative 1 to the 8 over 8 to the 3rd, that's 1 over 8 to the 3rd. And, that's the same as 2 to the 9, which is a number that they sometimes ask us about in AP Calculus. And we know that's 512. And now 1 over 512, that is the type of fraction that is definitely less than 1 over 500, so I conclude that I use 7 terms so that the 8th term is my error, and that error has gone under 1 over 500. Now let's look at some examples from recent free response problems. So in 2022 we had this one, and I think this one was tricky kind of because of its simplicity. Okay, so the function f defined by the power series here for all real numbers for which the series converges show that the absolute value of the difference between f of a half and a half is less than a tenth. Justify your answer. Okay, so I think the first thing we need to do is just kind of investigate the f of 1/2. So we're going to plug in 1/2 for x, and we're going to get, this series out here, which is an alternating series. Okay, but then this 1/2 right there. Now, if you see 2 things subtracted from each other inside absolute values, especially in the context of series, it's going to be an error question. So I think a lot of people saw that this was supposed to be an error question, but weren't totally sure about where to go from there. And I think what they wanted you to notice was that 1/2 was the partial sum that you would get if you used only one term. Okay, now, the highlighted expression in red, this is an alternating series whose terms decrease in magnitude to 0, which means that it converges by the alternating series test. And that means we can use the alternating series error bound on it. So we're going to say that error is, which I guess we could also characterize as the absolute value of the difference between f of 1/2 and 1/2. Okay, that's going to be no more than the absolute value of the next term. Okay? And we can see what the next term is going to be. It's going to be that 1/2 to the 3 divided by 3 made negative. Okay, so we're going to say, all right, well, once we take away that negativity, for the absolute value, we'll have 1/2 to the 3rd divided by 3, and that's going to be 1/8 times 1/3, and that's 1/24. They asked us to show that this is less than 1/10. They're not going to ask you to show it's less than 1/24 because that would make it too obvious what you're supposed to do. We're supposed to look at this and see 8 times 3, that's definitely bigger than 10. So 1/8 times 1/3 is definitely less than 1/10. And so we say that's less than 1/10, and we have justified our answer because we checked with the alternating series test. Right, now the last example I've got for you is a little more straightforward. So it's like, here's an alternating series. You're going to use the first two terms to approximate g of 1, and you're going to use the alternating series error bound to determine an upper bound on the error of the approximation. Okay, so the first thing we're going to do, if we're going to use the alternating series error bound and they haven't already told us that the series is converging about the alternating series test, we need to verify that ourselves. So I'm going to say g of 1 is alternating. The magnitude of the terms is decreasing, and their limit is 0. And you can say that with words, or you can show it out like that. It doesn't really matter, however you feel. And then if that's the case, then the error will be no more than the absolute value of the next term. So if they use the first two terms, then it's going to be the third term will go in there. Now the trick with this one is that n started at 0. So the first two terms are n equals 0 and n equals 1. So the third term will be the n equals 2 term. And so when I go and I plug in n equals 2, I'm going to get 1/2e to the 2 plus 3. If I take the absolute value, but I think even if I didn't, it was -1 to the 2 power, so it's going to be a positive 1 in the numerator. And that's going to be my alternating series error bound there. All right, and that's all the examples I've got for you. I think, 2 multiple choice, 2 free response, that kind of hit it from a few different angles. I think that's going to be all I need to show you. Between the alternating series test and the absolute and conditional convergence and the alternating series error bound, it can kind of be a lot. But I think if we, break it up into these chunks, that it makes it more manageable. And at this point, it's definitely you're ready to go and start practicing. So that's all for this video. Thanks for watching.